Okay, so today we will cover section 7.10, and then we'll also cover chapter 8 and chapter 9. And it feels like a lot, or I'm sorry, not chapter 8, it'll be chapters 9 and 10. Chapter 9, chapter 10, okay. It seems like a lot, but I think we can do it, okay? Alright, so section 7.10, this covers one test called the Wilcoxon MannWhitney test. Okay, this is equivalent to the Wilcoxon rank sum test. So if you ever take more statistics in the future, chances are and they cover this topic, chances are the Wilcoxon rank sum test will be the test that's covered. I think it's a little bit more common in the literature. Our textbook chooses to do a Wilcoxon MannWhitney test, and there's nothing wrong with that, but I feel like it's less commonly referred to. Okay. And okay, so before we get into this, let me just kind of explain the scenario in which it's used. So far we've covered the t-test, okay? And the t-test, we can compare the means of two samples, okay? So let me just recap. So we have the t-test to compare the means of two populations based on two independent samples. Okay, so this is what we covered in chapter 7. In chapter 8 we did the t-test to look at two paired data from paired samples, okay? But in chapter 7 we compared the means of two populations based on two independent samples, okay? And here, you know, our null hypothesis was mu1 is equal to mu2, okay? And all of our math and our conclusions were based on the t-distribution, okay? So conclusions, or I guess our p-value is based on the t-distribution, which is kind of like a cousin of the normal distribution. And this is based on the central limit theorem, okay? Based on the t-distribution, which ultimately depends on the central limit theorem. Okay. Does all of this kind of sound familiar? All right. Now, when we talked about the central limit theorem, I think I briefly mentioned some conditions that have to be true for us to apply the central limit theorem. Do you guys remember those conditions? Okay, so I'll write these here, all right, in case we've forgotten, which it sounds like we might have. All right, so conditions to apply the central limit theorem. Okay, so that's kind of like a sub thing. Okay, so conditions to apply the central limit theorem. So one is the sample must be random and independently obtained. Sample. Okay, and then number 2, we had the second part was the sample can't be too big. Sample cannot be too big. And we defined too big as over 10% of the population. So whatever your population is, you don't want to sample more than 10% of that. And then, but you know, we rarely violate this one, okay? Only if you have a small population. But it's this condition: the sample cannot be too small. Okay, and there were kind of two parts to say, you know, what does it mean to be too small? And one was, we said, if the population is normal, any sample size is fine. But if the population is not normal, we need a large sample. And the rule of thumb was something like 25 or more is generally a large sample. Okay, but then we also said, you know, if you have a really skewed distribution, then maybe 25 is still not big enough. Okay, hoping this feels familiar, okay, in our memories. Okay, so there's a question, you know, what if we wanted to do something like a t-test where we want to compare two independent samples, but these conditions are violated, so we can't apply the central limit theorem. Okay, so essentially what happens if so the Wilcoxon MannWhitney kind of answers like, what can we do if condition 3 is violated? It doesn't really tell us what to do if 1 or 2 is violated. Okay, and actually there's not a whole bunch of statistics you can do if condition 1 is violated. So if you don't have a random or independent sample, like you're just surveying your friends to try to make conclusions, you're not going to be able to do much. Okay, so if somebody releases some kind of survey results taken from an internet poll, there's not really much you can do with that. Okay, so I think there was a year when Time magazine tried to pick person of the year based on some internet poll, and it was like a complete disaster. So you know, so if condition 1 is violated, then there's nothing we can do. But Wilcoxon MannWhitney and Wilcoxon rank sum kind of tries to say, like, what can we do if condition 3 is violated? Okay, so if you know, condition 3, that is the quote large sample condition, okay, so basically if this condition is violated, then we cannot use the central limit theorem. Okay, and if we can't use the central limit theorem, we can't use the normal distribution, and all of this stuff essentially falls apart. Okay, so the Wilcoxon MannWhitney test or the Wilcoxon rank sum test falls under this category of nonparametric statistics. Okay, and so there's an entire field called nonparametric statistics. Okay, and you can take an entire class devoted to the topic of nonparametric statistics. You can devote your entire life researching nonparametric statistics. We're going to cover nonparametric statistics maybe in about 30 minutes in our class. Okay, this is about how much we're going to dedicate to it. But there's an entire field or subfield of statistics called nonparametric statistics, and basically this is, we are not going to apply any kind of assumptions about the distribution. We're not going to assume that the sampling distribution follows a normal distribution. Okay, and the reason why they're called nonparametric statistics is because things like the normal distribution and the t-distribution are defined by parameters, like the mean and the standard deviation and the degrees of freedom. So those things define this theoretic distribution. As soon as you're given these parameters, you know the exact shape of the distribution. Okay, so parametric statistics, like the t-test, depend on these mathematical theorems like the central limit theorem and stuff. Okay, so non-parametric statistics, basically, we will not apply assumptions about the distribution of our population. Okay. Or we will, I guess, not apply, I guess we will not make assumptions about the distribution of our population, I should say. Okay. And so, effectively, this allows us to compare two samples. So with I'm going to just abbreviate the Wilcoxon MannWhitney test as WMW. With the Wilcoxon MannWhitney test, we can make comparisons between two samples without the need to assume that the sampling distribution is normal. Okay, so again, the sampling distribution is kind of the distribution of y bar, right? So, well, you know, on a practical level, practically speaking, this means use the Wilcoxon MannWhitney test if you have a small sample, if you have small samples, so, you know, less than 25, and there are some outliers, within your sample. Indicating that the respective population is not normal, okay? So if you have small samples and there are outliers in the sample, then this would be a good time to use the Wilcoxon MannWhitney test. Okay. Otherwise, you're better off doing the t-test. Okay. So last week, did I talk about statistical power? No. Okay. So I'll mention this. But I did talk about alpha and I did talk about beta. Okay. So. All right, so, okay, so in general, non-parametric tests are less powerful than their parametric counterparts. Okay, so for example, we have the parametric test, which would be the t-test for independent samples. Okay, and then the non-parametric would be the Wilcoxon MannWhitney test. So what it means to be less powerful, okay, less powerful means you are less likely to reject the null hypothesis when the null hypothesis is false. Okay, so the power of a test is a good thing. We want to maximize the power of the test, meaning if someone if someone has cancer, we want our tests to be able to detect that. Okay, a high power test with high power would reject the null and come to the conclusion, someone has cancer very often. Okay, you don't want to make your test so powerful that your alpha, by making your alpha really high. Okay, that's not a good way to make a test powerful. Okay, because alpha is kind of the false positive rate. So you could make a test powerful by increasing your alpha. Okay, if you make alpha 100%, basically you're just telling everybody you have cancer, and that's not useful. Okay, because this is not that's not helpful. Ideally, you can keep alpha low, but your power is high, so you can assure people who are cancer-free that they are cancer-free, and anybody who has cancer you correctly identify as such. So anyway, a non-parametric test is generally less powerful, meaning even when the null hypothesis is false, you don't have a good chance of correctly identifying that. Okay, but it would be incorrect to apply a parametric test in a situation where those assumptions are not true. Okay, so when you can't apply the central limit theorem, the conclusions, and you use the parametric test, your conclusions would just be wrong. Okay, well, I shouldn't say they would just be wrong, but your conclusions are not based on a statistical reality. Okay, it would be a dangerous thing to do. So you have to use a non-parametric test, but in general they're less powerful. So you need to have more convincing data in order to make the same type of conclusion. Okay, so this is kind of when we would apply the non-parametric test, and so what we do is so here's a situation where we can apply the Wilcoxon MannWhitney test. Okay, so we are going to so our data comes from soil respiration data. I guess that's written right here. So apparently we went to the forest and we looked at soil, and we had some kind of device that measures how much carbon dioxide is given off by the soil or something. Okay, and here's I don't know why I'm telling you this, but have you ever thought about like where leaves come from? Like, where does the matter that build a leaf, where does that come from? Where does it come from? It comes from the air. It comes from the air. So so you have trees and you have stuff. It's not like it's pulling nutrients out of the ground and building a leaf. Okay, the leaf breathes in carbon dioxide, and it takes the carbon molecules and it releases oxygen, and so the carbon dioxide in the air is what forms the leaf. Okay, it's not trying to, like, it does need roots and for water and all of this other stuff and some of the nutrients to go up the tree, but the primary source of where the matter for the leaves come from the air. Anyway, side fact, You just go to YouTube. Where do leaves, how do trees grow? And then there's like carbon footprint offset initiatives where you go on an airplane, but then you pay an extra $10, and they say we're going to plant 100 trees for you or something. It's good that we're planting trees. Okay, soil respiration data. So this is what we've done. We've gone to two parts of the forest. Okay, there's an area in the forest where there was a gap in the growth, and we measured the carbon dioxide respiration. Okay, and then we went to an area where there was growth in the forest, and we measured the respiration data. And so what we see over here in the growth data, we have big numbers like 315, 190, 170. It's even hard to tell kind of like what's an outlier, because some of these are like really huge. But if you look over at the gap data, they're kind of like very well behaved, and they're in this much smaller range. Okay, so this would be a good candidate to use the Wilcoxon MannWhitney test. Because we're not making any kind of assumptions about the distribution, the populations from which these come from, our null hypothesis cannot be written symbolically, okay? Because there's no symbols involved. There's no parameters. So we have to say something like the population from which, group 1, the growth data comes, okay, and then has the same distribution as the population I should just say that produces the gap data. I don't know why I'm saying from which. As the population that produces the gap data. Okay, I guess I could have written that for the first part. The population that produces the growth data has the same distribution as the population that produces the gap data, or from which this data comes from. Okay, that's fine. All right. The alternative can be something like the population that produces the growth data. Okay, and then we can have, so I'm going to break this up, and I'll make non-directional, the non-directional equivalent, and then the less than equivalent or the greater than equivalent. Okay, so this will be the population that produces the growth data has a different distribution from ... or tends to produce smaller values than, or tends to produce larger values than, okay, and then it will be the population that produces the gap data. Does the way I wrote this make sense? Okay, so here's, I've basically written three statements here. So one, if you wanted a non-directional alternative, it would be the population that produces the growth data has a different distribution from the population that produces the gap data. Or if you wanted an equivalent to having a less than sign, in your alternative hypothesis would be the population that produces the growth data tends to produce smaller values than the population that produces the gap data. Or the population that produces the growth data tends to produce larger values than the population that produces the gap data. Okay? So in our case, well, we're supposed to come up with the null and alternative hypothesis prior to looking at the data. But it would make sense to try to use this greater than alternative, where we're saying the population that produces the growth data tends to produce larger values than the population that produces the gap data. Okay? And so again, we are not using any kind of symbols. We're not saying that the mean of this population is larger than the mean of the other population or anything like that. We're just saying this population tends to produce values like this, and this population tends to produce values like this. Okay? The null hypothesis says that these two distributions are the same, essentially, and then the alternative says one of these is making bigger or smaller values than the other. Okay. So this is how we write our null and alternative hypotheses for a non-parametric test. Okay. So do not use symbols like mu in hypotheses for non-parametric tests. Okay. All right. So then, so we have this, and then we'll. So here, I'll just write it out. Population of growth data. So we will pick this one, tends to produce larger values than population for gap data. Okay, so once we've established our hypotheses, we will we'll talk about carrying out the test. Okay. So I'll show you how to calculate the test statistic and then get the respective p-value. Okay. The respective p-value from the Wilcoxon MannWhitney test or the Wilcoxon rank sum test, these are based on the from all possible rearrangements of data. Okay, so it's like I guess I'll talk about this after I do it. The theoretic part, it doesn't really matter. Okay, so what we're going to do is we're going to, step one is we're going to arrange all of our data in two columns. Okay, so arrange the data from least to greatest. So we will do this for and leave a little bit of a margin on you know, to the left of your growth column and to the right of the gap column. Okay. All right, and so all we're going to do is we're just going to go from least to greatest. So for growth, it's go 17, 20, 22, 64. Wait, 17, 20, 22, 64, 170. 190, 315. Same thing for the other side. 6, 13, 14, 15, 16, 18, 22, 29. Okay. All right, and then what we do is for each value, count how many numbers in the other column are smaller than the value. Okay, and then ties are worth 0.5 each. Okay, so I would go, for this first value I look at 17 and I go how many in the other column are smaller than 17, and I go 1, 2, 3, 4, 5. All of these 5 values are smaller than 17, so I would write 5. And then I go to 20 and I say how many in this column are smaller than 20, and I've got 6 values in the other column are smaller than 20. And then when I get to 22, I have 6 values that are smaller and 1 value that's tied. So each tie is worth 0.5, so I would write 6.5 here. If there was another 22 in this column, it would be 7, because each tie would be worth half a point. Okay, and then at 64, what do I have? All 8 values are smaller, okay, and that's going to be true for all of these other values. They're all going to have 8 values in the other column that are smaller. Okay, so one thing to note about non-parametric statistics is that the magnitude doesn't really matter as much, okay? It's just, is it bigger or smaller? All of these values, 64, 170, 190, 315, they're all going to contribute the same amount to our final test statistic. They're all going to contribute 8. So even if this was like a billion or only, 65, it would contribute 8 points to the calculation of our test statistic. The comparison is that parametric tests are like business and non-parametric tests are like sports. So in business, it matters if you lose 1,000 or if you lose 10,000, because you'd be angry if you lose 10,000. But with sports, if you win by 1 point or if you win by 50 points, it doesn't really matter as much. A win is a win. Okay. So over here, okay, with gap data, we look over here and we say how many in the other column are smaller than this, and we say 0. At 13, all of these numbers have 0 values in the other column that are smaller. Finally, at 18, we have 1 value that's in the other column that's smaller. At 22, we have 2 values and a tie, so we have 2.5, and at 29, we have 3 values that are smaller. Okay. All right, and then so once you do that, you add up, you sum these columns. Okay, you sum them. So here we have 6.5, and over here we have 49.5 if you add them up. Okay, so add these up, and then the larger value is your test statistic. So the larger of these 2 values will be our test statistic. So our test statistic, which we have labeled U for this test for whatever reason, is going to be 49.5. Okay, so add up these values. Okay, and then the larger value is the test statistic. Okay. We will have, we look this up in a table specifically for the Wilcoxon MannWhitney test, okay? And to look it up, you need to find the appropriate row, and the rows depend on the size of your 2 samples, okay? So you have a n and you have an n prime, okay? So basically you've got, n1 over here, we have 7 values. And then n2 we have 8 values. Okay, so what we do is we assign whichever of these 2 values are larger is gets assigned n. So this is the larger of n1 and n2, and then n prime gets the smaller of n1 and n2. So what we have is we've got test statistic U of 49.5, n will be 8, and n prime will be 7. And then we look this up in our table. That's it. Okay, so where did my reference table go? Okay, so we go to table 6, critical values for the use statistic of the Wilcoxon MannWhitney test. So we go to n is 8 and n prime is 7. Okay, and then it lists off in bold print test statistics and the corresponding p-values. So what we have is that if our test statistic, where did it go? If my test statistic were 50, then I would know that my p-value would be exactly 0.0093. Okay, but here I get a test statistic of 49.5, so all I can say is my p-value is somewhere between 0.021 and 0.0093. Okay, but again, if you had one of these exact values that are printed in bold, you would know your exact p-value. Okay, which is relatively, it's more common for the Wilcoxon MannWhitney test than the t-tests. Okay, so all we can say is our p-value is somewhere between. Oh, I'm sorry. Let me hold on. Okay, so these are our tail areas. Okay. This is for non-directional alternatives. If we had a directional alternative, we take these italicized numbers and we divide them by 2. Okay, so there's kind of a little. I know this is the opposite of how the t-table works, and so there's kind of a note to remind you as such for this. Okay, so here this says for a non-directional alternative, our p-value would be between 0.021 and 0.0093. Okay, so from the table, for a non-directional alternative, the p-value would be between, what was it, 0.021 and 0.0093. Okay, I think we have a directional alternative, something like growth data is larger than the gap data. Okay, and we should, anytime you have a directional alternative, you should verify that directionality is met, which it is. Okay, the sum for the growth data is 49.5, indicating that there were much more values in the other column that were smaller, and over here, this one's only 6.5. So we have a directional alternative. We have a directional alternative. The directionality is met by our data. Okay, so our p-value is between 0.0105 and whatever 0.0093 is divided by 2. 0.0047 or 465. Okay. So we have a directional alternative, and the directionality is supported by our data. So our p-value is half of half of what's given in the table.
Wait, I'm confused. So is this example a non-directional or directional?
It's directional, because in the on the previous thing I said the population of the growth data tends to produce larger values than the population of the gap data. Yes.
So are we not setting up our p-value like we do the t-test? with 0.02 less than p, which is between 2 or 1% or something like that?
Oh, we are. We're essentially saying our p-value is less than 0.0105, but greater than 0.00465.
Okay, so this number's all the way at the top.
Yeah, yeah. So yeah. We're not using the column headings, okay? Because so the Wilcoxon MannWhitney test depends on like how many, the count of the other column that depends on this. It's these p-values follow kind of like a discrete distribution. So it's not continuous. You're not going to have 48.227 numbers in the other column. You'll really only have a whole number, except in the case of ties, where we've decided we're going to award half a point each. Okay, so so this is how it goes. All right, and then so we would reject the null hypothesis and say we have evidence to support the idea that the population that produces the growth data tends to produce larger values than the population that produces the gap data. Yes?
So we don't use this as the...
Yeah, you don't use the column headings. Just use those italicized numbers. Okay?
Wait,
But
why are you rejecting the...
okay, so here I'll so what we got from the previous statement was our p-value is between 0.0105 and 0.00465. Okay? So, if alpha is 0.05, our p-value is less than alpha, okay? And so that would lead us to reject the null hypothesis, support the alternative, okay? So we say, our data supports the alternative. So, this kind of goes with any kind of hypothesis test, really. And then so at this point we say, our data, or we'd say we have evidence that the alternative is true, right? So we have evidence that whatever the alternative statement was saying, which was we have evidence that the population that produces the growth data tends to produce larger values than the other population. And the population for the gap data. Okay. Yes?
So the alpha statement, the second statement you made, we're under the assumption that we were testing on a 0.05 alpha, or?
Yeah. I mean, we didn't say anything earlier, so kind of assume alpha is 5%. And so there you go. Let's see. So I don't know if you care where these numbers in your Wilcoxon MannWhitney test table come from. They come from, if you look at all of these values here, okay, basically we're saying, let's say we produced a total of 15 values, okay, and if the null hypothesis were true, meaning that all of the values are coming basically from the same population, then essentially what ends up in the growth column and what ends up in the other column is a product of random chance. Okay, and so effectively these hypothetical values are generated by saying, let's say I just take all 15 values, I shuffle them up, and I just randomly deal them out into two columns. When I randomly deal them out into two columns and I perform this test action where I count in the other column how many values are smaller, Okay? Most of the time, when I count up how many in the other column are smaller than this value, and how many in this column are smaller than these values, when I add them up, I would get test statistics that within a certain range. Okay, so if I looked at 17, I'd probably expect only 1 or 2 values in this column that are smaller. And when I look at the largest value over here, I'd expect most of the values in the other column are smaller. But not something like this. I'd probably expect a value of around 28 or something. But we can keep shuffling this over and over and over again and see how often do I get a value like 49.5 by random chance. Okay, and it turns out that if you did this study, you would get that value of 49.5 between 1% and 0.5% of the time, and that's where these table values are coming from. Okay. If you don't care where the table values are coming from, don't worry about it. Okay. That's but. Yeah, I guess I hesitate to just say, hey, this is how you do it, the end. I think the key, but knowing exactly where these values are coming from, probably not as important as knowing when you should use the Wilcoxon MannWhitney test. Okay, so when do we use this non-parametric test? We use it when we cannot apply the central limit theorem. So specifically when we have small samples, but we also have something that indicates that our population is not normal. So if you see outliers in your sample, then it's probably your population is not normal, so a small sample will not do.
Is there any other terminology other than tends to produce that we should know about for this one, or is it just is that the keyword?
That's kind of just that's like the generic statement of saying this population is larger than the other population, without saying something like the mean of this population is greater. Yeah. Yes.
Will this test work on a paired test or paired sample?
Yeah. No. So the other parts. So we're skipping pretty much the rest of Chapter 8. So in Chapter 8, we just did the t-test for paired data. Okay. If you look into Chapter 8, they cover non-parametric tests for paired data and all these other things, which is fine, but I feel safe skipping it. Okay, and I don't feel like I'm cheating you guys out of your statistics education, but they are there, and for your reference, if you keep your textbook, you can look that up, and that's there. So and then you also have the Google, and you just say, I need to do a parametric test and I have paired data, and then it'll say like, hey, here are some tests you can do. Okay, so this is kind of our full exposure to non-parametric tests. That's about it. So I guess it's good to know that these tests exist if you can't apply these assumptions here. Okay, all right, let's take a quick break, like 5 minutes, stretch break, and then and we'll come back and we'll cover chapters 9 and 10.